just record to the
Yeah, that's fine.
record to the cloud. I don't know what that means, but okay, I'm gonna sorry, John, this is Hendrik Hamann. John's the other postdoc. Me and John are running these seminars together.
Nice to meet you, and thank you so much for coming. We're looking forward to your talk today.
All right, thanks, John. Try to make it entertaining.
Yeah, so I guess we're all set. I already started recording. Hendrik has already practiced sharing his screen, so we can just hang out and relax and start. Anyway, I'm just so thrilled for you to be here, Hendrik. Personally, I'm coming from a machine learning and robotics background, and I got my PhD at the Robotics Institute from Carnegie Mellon. Now I just started my postdoc here at NYU, and I'm working in medical robotics, rehabilitation robotics. But I always say that my dream is either to apply robotics and machine learning either to medicine or to climate change. So right now, because I feel like these are the two most humanitarian things we can do. So I picked medicine for now, but part of me also wants to maybe at one point during my career do some work in climate change. So I'm personally very excited to have you here. And it's also exciting that you're also in New York, and
yeah, that's right. Just up the hill. I think I gave a presentation at CASP 3 years ago. Or 4.
Okay.
Yeah, so it was down. You guys are in Brooklyn, right? Still.
Yes, we are in Brooklyn in the Metro Tech Center. Yeah.
Yeah. So I'm sorry, I will not have a whole lot to say about robotics.
Oh, that's okay.
Although we have under the Future of Climate actually a program which focuses on discovering and finding new materials for carbon capture using AI. So it's basically, there's a bunch of technologies involved, but there's a validation part to testing these new materials for their carbon capture potential. And that's a big, gigantic robot, which we have in our Zurich lab, which then tests these materials through for certain properties, and then that's fed back into these AI models and so on and so forth.
Yeah. Well, a lot of the work I've done is just been purely in the perception aspect of robotics. So it's just how do you take data and then run machine learning on it? So, and then sensor fusion as well.
So
I would,
a lot of the work actually, not so much today, but a lot of the work we're doing, of course, in climate related is at its heart, it's a gigantic data fusion.
Exactly, yeah.
At its heart, there's nothing, that is the challenge. And how do you do this at petabyte scales? That's a lot of climate modeling is exactly that, right?
I would love to, I'm going to start letting people in from the waiting room because I feel bad hogging you to myself, but I would love to speak more with you in the near future. I would love to just learn more about what's happening at IBM and be in contact with you.
All right, yeah, no worries.
Yeah, I'm going to admit Yuri here because Yuri.
Yuri, no, you should not admit him. I think we should make sure he's not attending.
Hi, Yuri. Jerry, are you there? Hi. Okay. Hi. I admitted you first before everyone else, so you could say hi since you were.
Hendrik, hi. Jackie, how are you?
Hi.
I recommended not admitting but they wouldn't listen. They wouldn't listen.
Hendrik, you've always been a great supporter. Thank you. Where are you? Are you at home, Hendrik?
Yeah, I'm at home.
Oh, geez, I'm at NYU. Is that where you are, Jackie?
I am here in Costa, NYU at 370J. Where are you?
I'm at the same place. I'll come by and see you.
Okay, yeah. Just so you know, I actually have a meeting right at 1 p.m., but maybe if you could come at 2 p.m. I mean, yeah,
Will
like
do.
2 or 2:30, I'll be done. Yeah. Okay.
Henry, I like your hair.
You know,
Yeah.
I don't know what happened. Yes, I got up this morning. It was like this.
Wonderful. So I just let in some participants, and maybe we'll wait a few more minutes to let people join. Looks like we already have a good audience here.
Hi, everyone.
Hi, Juan.
Hello, Hendrik.
Hello.
Thanks for joining us today.
Very nice to meet you.
Nice to meet you. Looking forward to the talk.
Thank you.
Juan, I'm sure, as you already know, is the director of COST. So.
Great. Yeah, I met your previous, Steve, your previous director, last time I gave a presentation.
When was that? What year?
3 years, maybe. Cool. Yeah, 3 years ago or so. Yeah.
Excellent. Yeah. It's a shame that we cannot have you here in person for today, but you know, it's still, you get a chance to interact with the community. So
yeah. Well, thanks for having me.
Thank you.
Okay, so well, Juan, do you think we should get started, or do you think I should wait a few more minutes to let people join?
Maybe we can start with the intros and everything, and then people will be joining in the next few minutes, I'm sure.
Okay, great. Yes. So I would like to introduce Dr. Hendrik Hamann. We are very honored to have him here. He's coming from IBM Research. He will be speaking about strategies for combating climate change, including carbon footprint reduction, preparedness, planning, response, and resiliency, leveraging technologies in hybrid cloud platforms and AI to exploit massive generation of climate-related observation and simulation. Using recent advances in AI, big data analytics, geospatial indexing, and cloud platforms. Dr. Hamann is the IBM Chief Scientist for the Future of Climate Change. He received his PhD from the University of Göttingen in Germany. In 1995, he joined JILA, or JILA, which is a joint institute between the University of Colorado and NIST, and he developed technology which is the basis of all of today's high-resolution near-field microscopes. In 1999, he joined IBM T.J. Watson Research Center, and he developed technology there, which is commonly referred to as TAR, or TAR, which stands for Thermally Assisted Reporting. And this is the foundation for being able to push storage densities of magnetic hard drives. And during his time there at IBM, he's also contributed to technology that today is in every high-performance hard disk drive. Since 2001, he's leading the physical analytics program at IBM Research. One of Dr. Hamann's main accomplishments for IBM are the invention and development of IBM's measurement and management technologies, or MMT, for improving energy efficiency of data sensors in buildings, which have now been deployed worldwide in IBM technology. His interests include sensor-based physical modeling, machine learning, artificial intelligence, big data analytics, geospatial analytics, climate informatics. He has more than 200 peer-reviewed scientific papers. He holds over 170 patents, He has served on governmental committees, including the National Academy of Sciences, the National Science Foundation, and he's an industrial advisor to many universities. He's won several awards, including the 2016 prize for the Industrial Applications of Physics of the American Institute of Physics. He is a member of many societies, including the American Physical Society, the Institute of Electrical and Electronics Engineers, the Optical Society of America, and the New York Academy of Sciences. He's also a standing member of the National Mapping Committee of the National Research Council and a visiting professor at Yamagata University. So with that, I am very honored to hear Dr. Hamann's talk today. Take it away, Dr. Hamann.
Okay, so I think you let me, can you give me permission to share? Oh no, I can't, no worries.
Oh, okay.
All right, let's take it away. No, thanks so much for this introduction. I had no idea that I did all this work. sounds like a kitchen sink. Everything in the kitchen sink list.
No, it's very...
But I'm super delighted to be here. We talked before about this. If there are questions, I usually prefer questions in between if they're not too long. So feel free to ask questions if you really have some. So let me just say a few words about IBM Research, and then I will talk about the future of climate and then specific research we are doing or technology development in this area. Yeah, so I'm from IBM Research. We are roughly 3,000 researchers around the globe. You see here the locations of the actual labs. The main laboratory is actually not far from where probably most of you guys are. It's just 40 miles north of New York City, here in Yorktown Heights. We have been here for over 75 years. Some, of course, may think, well, IBM, its legacy and so on and so forth. But I think through research and innovation, we actually have been able to reinvent the company many, many times. And so that is a role of research in IBM. And it's not just internally focused on impact we can have for the company, but we're also trying to contribute to the sciences, right? We are kind of proud that we have, of course, Nobel Prize winners among our colleagues and so on and so forth. Now, if you look into IBM Research, there's so many different things we're working on. So you can imagine technologies for AI, hybrid cloud compute, quantum computing. So series of initiatives around healthcare, etc. Today, we'll talk about what we call in IBM Research, the future of climate. And it's really around taking science and technology to apply them to helping with the adaptation and the mitigation for the impact of climate change. Now, of course, why are we interested in this? For multiple reasons, and I'm stating the obvious. The economic cost of climate change is, of course, enormous. And so this is just an example. Our colleagues at Swiss Re, which is a major reinsurance company, have been estimating the economic loss due to climate change, if nothing really drastically happens, to be around 10% of the total economic value. And so we are talking about tremendous numbers. I think also everyone starts realizing that climate change, you know, while some people think this is way in the distance, now climate change has been accelerating, right? It's on the order of 100 times or 1,000 times faster than what we've ever seen. So to a large extent, it's already here. It's not something which is going to happen in 10 years, in 20 years. And some of that we start seeing. Now, if you look a little more detail and more in detail, it's interesting that to look into why businesses, organizations are responding to climate change. And I think in general, it is the public at large, right? The public informed in form of investors. You probably have heard about this environmental and sustainable conscious investing. So there's a huge pressure on businesses to disclose the carbon footprint, to understand the risk to climate change. There is huge pressure from consumers. So the public in form of consumers are really demanding businesses to become more sustainable. They're looking for sustainable products. And then finally, of course, we're voting different governments in place. And we see this all around the globe. And the voters, the public, they're demanding a response to climate change, right? So there are massive initiatives in Europe, in China, and of course, also here in the United States. Now, because of all these reasons, the pressures which organizations face and the way IBM thinks about, we think about how we can help and contribute. We have this research program, which we call Future of Climate. And today I will just focus on a few components on a few aspects of this program that I felt like maybe I can just briefly outline what are the sort of the core research pillars which we're driving. Everything in the Future of Climate is organized around mitigation or adaptation, right? So on the mitigation side, we're looking into technologies. How can you perhaps capture carbon, right? What are the technologies to capture carbon? So there is this relatively large project where we're looking into using AI and advanced machine and other advanced techniques to identify new materials and processes to capture physically carbon from the atmosphere, or to reuse carbon dioxide for other materials like plastics and so on and so forth. Now, we do a lot around carbon, what we call carbon performance. Right, so today, most businesses are looking into the carbon footprint, or even individuals are looking at the carbon footprint. Now, accounting for your carbon footprint is a start, and that's why we're calling it carbon performance, but it's much more important, of course, to understand how you can improve on that. So when we talk about enterprise carbon performance, we're really doing research in scope 1, scope 2, scope 3 type of reporting, basically getting the right accounts of the carbon footprint through the whole enterprise, which of course includes the whole vast supply chain and others, but then also how can you optimize the performance and how can you optimize this integrated into business processes. Because IBM is in the hybrid cloud business, we have a special program which focuses on optimizing carbon footprint of hybrid cloud compute, right? You think about cloud computing, it's complicated because you have shared resources, you have virtualization, you have the whole stack, you have network traffic, you have data movement. So how do you account for the carbon footprint? And then how do you optimize or reduce the carbon footprint through controllers? So this is all what's happening on the mitigation side of things. Now on the adaptation side, we're looking into geospatial technologies, especially as it relates to climate modeling and climate impact modeling. And I will talk about this a whole lot, so we get into the details later. But think about it as an underlying information architecture, as a technology, not a science project. So we're really building and developing here an underlying information architecture which helps to accelerate climate modeling. On top of that information architecture, we have accelerators, AI-enabled accelerators. So to touch on that really briefly, which helps to accelerate the modeling of climate impact and other climate-related things, downscaling and so on and so forth. And then finally, we have a whole set of climate-aware applications. I will not touch on that, but all this is, of course, being driven to eventually build applications to help organizations, businesses to make better decisions, to prepare for the impact of climate change. Okay, so as I said, today we focus on accelerating the geospatial aspects of climate modeling. And you want to ask probably first, why are we focusing on this, right? Why do we think this is important? And why do we think we, IBM, as a technology company, can make a contribution there? And there are basically three premises this is based on. The first one is a very obvious premise. If you think about climate change and its impact, it's clearly spatial temporal or geospatial temporal. So climate change is happening at different levels with different risks, with different impacts at different places at different times. So fundamentally, it is a geospatial use case, you would almost think about this. So that's the first premise. The second premise is, of course, we've heard this before, but there is a growing evidence that AI can actually play a critical role in helping us to accelerate climate modeling, to improve climate modeling, to improve our forecast, to improve impact predictions. This is from a paper, which is not from a paper, it's from an article where the opportunities of AI as it relates to machine learning is highlighted as it relates to climate change. Okay, so we have the third premise is, so we talked about the fact that, yes, climate change is geospatial. We talked about the fact that AI can play a critical role. And then thirdly is that the underlying information architectures have not kept up to date with all the data which has been gathered about our climate. So there's an interesting paper here on the left side you see. It comes from, it's actually a while back, 2011. And even in 2011, that tells you, of course, a lot of these ideas are not brand new, but a lot, they're talking about the need for a new paradigm of a new data system. Now they make some predictions where they show how the data for climate-related data, satellite data, modeling data, and so on and so forth has been growing. Now it's interesting to see that these predictions are vastly wrong. Still, their point is well taken, which is something they published in Science, that indeed the underlying information architectures, the existing systems are being outpaced by this massive amount of data. I will talk about this a little bit, what that means and what are the opportunities for acceleration. There's another thing which I just grabbed from a consensus study, I think from the National Science Foundation. Again, recognizing that our existing information architectures, which we use for Earth observations, climate research, etc., have not kept up to date, despite all the progress. It's not meant to say that there have been no progress. But if you take this all together, saying, okay, AI is a key driver. So what makes AI really function? It is the underlying information architecture. So that's what we're going to be focusing on. This is another way to put this. If you think about what are you doing as a researcher in climate research, in many cases, you're going to have some question you want to answer, some hypothesis. You're going to go out and find some data from these archives of data. You're going to do some integration and simulation. Eventually, you're going to do some featurization of that data. You're going to feed this into a model you may build. It may be an AI model, maybe a physics model, maybe a combination of it. Eventually, there's going to be some visualization. You're going to do an experimentation, a validation, and that will help to answer your question. Of course, you're going to go around. It's not such an orderly process, but at the end, this is some of what you're doing. Now, the argument here is or the assumption of this research we're doing here is that over 90% of the time is actually spent on some of these somewhat not so sexy sounding topics of finding data and pre-processing and featurization. But 90% of the time is being spent there. And in fact, it is so bad that I would argue that in most cases, 90% of the time is being spent here to answer a specific question. In addition, we're only using probably only 0.1% or way less of the available data, which we could be using to answer that question. Now, given the importance of that, that's really why we're doing this research. Now, having set the stage, let me just say a few words. Why is it actually difficult to, what are the challenges to build an information architecture which would allow us to reduce this 90% on this pie, on the circle you've seen, to 5% or something of your time? And it has to do with multiple facets. The one facet is, if you think about climate data and geospatial information, it's somewhat complex for many, many reasons. And it goes a little bit beyond what is on these charts. But of course, it has multiple modalities. So there's representation, right? How do you represent information? So I can represent a watershed through vector information, through vector representations. I can have raster, so imagery information about this. I can have three-dimensional vector information. I can have, of course, time series information. The actual information, let's say it is a satellite measurement, it's a hyperspectral satellite measurement. There's going to be noise. So it's complex, and that's a challenge. But that's not the only challenge. The second challenge is, I kind of alluded to that, is that the size of the data you're dealing with is incredibly big. And I know a lot of people talk about big data, and a lot of people are thinking, oh, big data problem is being solved. I would argue, as it relates to climate change and climate applications, that's not the case. For example, people who are working in this field, they're probably familiar with the data sources, it's public data actually, so the European Space Agency. Of course, we have in the US, NASA, and so on. So it's just an example. Today, they generate tens of terabytes. So that's a lot of bytes, 10 to the 12 bytes, 10 to the 12 bytes a day. And that is quite big. This amounts to petabytes of information. That's just one space agency. That's just one data product. So this is ballooning incredibly. Now, at the same time, this is very high value information. And this is just one example. There are hundreds of these space agencies. There's a private sector who's actually start digitizing our physical world, right? So satellite observations, companies like Planet, and so on and so forth. So it's growing and growing and growing. And what are we doing about this growing? Right? So it's complex information. It's growing like crazy. So that's what we're going to be talking about. But before we do this, let's think about this for one sec, right? So it's complex data. We got that. Okay, but maybe people are going to say maybe there's lots of complex data everywhere, but it's really big. The other thing you have to realize is that these big data sets are so big eventually that you cannot move them, because you just do the calculations and you say, how long is it going to take me to download this data? And even if I have multiple connections, they are fundamentally, even if I have it on the same compute system, even if I have it in the same cloud, all this data, you're going to find out, if you run the numbers, that indeed this data is so big that it becomes almost unusable. And with the existing technologies, and the existing technologies all are trying to move the data to the analytics, the application. So I call this effect somewhat data gravity. And why do I call it data gravity? I call it data gravity because if big data sets cannot be moved, and I want to analyze and I need some additional data, I'm going to move that smaller data to the bigger data. So that's like gravity, right? So gravity tells me bigger mass attracts a smaller mass. And so it gets bigger and bigger. And so this whole notion of data gravity is actually, it exists in other areas, but I think it exists, and it is a great example of what that means in terms of information architectures for climate data and geospatial data. Here's the other thing. If you think about now all these climate data sets, and if you think for 1 second about, for example, satellite observations, right? Satellite observations, whether they're hyperspectral in the visible range, or you have great radio frequency satellites, which can measure water content and so forth. So if you think about all that data, so how is it being managed today? Well, people store this information, this satellite information, by scenes, by tiles, by file, by object. So you have picture by picture, basically. Now you think about it, right? So even if I have it on the same cloud, and I have satellite observations, and I have consecutive satellite observations, let's just assume for the last 10 years, and I have them on a weekly basis. If I wanted to get the time series, I have to open all the ones, right, over the last 10 years, because how do I get the time series? So it's just, it's a very spatial indexing, if you want. It's a very poor index, if you want, because even if you want to find something within all these images, you would have to open these images, see whether what you're looking for is in these images. And if it's not, close and go to the next image. Now you can parallelize that, but it's still inherently slow, because at the end you're stuck with the picture size. If it's a 10 megabyte file, you got to open that 10 megabyte file, and to open a 10 megabyte file, even if it's on your same hard drive or on the same cloud, you got to push it from the storage device all the way to the processor. Okay, so I told you about why we're doing this, why we think it's important, what are the current inhibitors. Now, next is what have we done about this? So this is work which started actually even way before we started looking into the future of climate. So we built this platform, I call it platform, but we built a system which tries to address these challenges, right? It tries to address this challenge of data gravity. So how can we overcome data gravity? How can we process petabytes of data within minutes? How can we help really researchers like yourself, perhaps, to do a better job in doing that? What can technology offer? How can we integrate all these different data sources? So that is really the reason why we built this system. Let me explain shortly what that system is today, and then I show you a little bit what's under the cover. Okay, so today, this system is doing the following, right? Because data gravity and data integration is so complex, we have built an industrial level data curation ingestion service. And what does that service do? It basically feeds data into our platform. It's a cloud-based platform. It's an IBM cloud-based platform where we basically have high-speed connections and other technologies. And often we work with data and content providers where we push data, which comes in all these projections, resolutions, and whatnot, right, into our system. And while we're doing this, we basically curate that information so it becomes analysis ready. That's what we do here. So, and it's a system which adds on the order of 10 to 15 terabytes a day. It does it in real time because new data becomes available, right? New weather information becomes available every day. New satellite information sometimes becomes available every 5 minutes, etc. So it's a system which is close to real time. It has these pipelines, and in these pipelines to all these different data providers, we make sure that we can get access to that information as fast as possible. We do the curation, which means it's a data integration, and we do some indexing. I'll talk about this indexing in a second. So once we've done that, all that information is in a key value store. It's a massive distributed compute system. We have on the order of 200 data nodes. We started 8 years ago with 3 different servers. Now it's almost a whole data center full. That's where we keep all that data in a key value store. And I tell you in a second what that means and why it is good. But it is good because through a key value store, you basically get away from this picture tile by tile problem, right? You basically create a key. The key has a location information, time information, it has some metadata and something else. And then you have the pixel value. You have the value of the measurement. Let's say it's a satellite measurement. So getting away with all these tiles and pictures, it's one continuum. And if you want to get the time series, it's very fast because you don't have to open the big tile. The other reason why this is super efficient is because it's a key value store. And you can use a Hadoop framework or something where you start chopping up all these data blocks, which means it lends itself to connectors like MapReduce or Spark, and you can parallelize all that processing, and that really speeds it up. On top of that, we have services. Don't go too much into these services in a second, but will, on top of this massive curated data, which now where you can now parallelize compute and AI workloads, you need a layer which helps with workflows, with people who want to get access to the data, they want to query the data, they want to run some models. And so this is all being done on this level. This is probably not so much of interest to you, but of course, from a commercial perspective, maybe that's, we dealing with data governance, and of course, there are marketplaces coupled to this, but then everything is accessible through an API, and you let me just highlight one feature, sort of going a little more into detail what the system does. If you go back to the chart, you see that there are different services for sitting on here, okay? Now, these services, if you, for example, today as a researcher are trying to access data, in most cases, that access is batch mode driven, meaning you submit something, you say, oh, I need this data, or you're going to an FTP site, or there is a process to that. So we have some real-time services. And it is actually quite an innovation, if you ask me, because what it does is, it actually is a way to connect a real-time service to over 6 petabytes. This is how much sits in the system today, 6 petabytes, to a real-time GeoServer. And GeoServer is an open source tool which allows you to really get access in real time. So how does it work? So first of all, of course, we have the classical way of doing batch mode, querying and analyzing, which is through a highly parallel MapReduce framework where you have a query, you want to find some data, and you don't know exactly, you just know I want, for example, satellite data where whatever certain features are such and such, and also weather data was such and such, and you want to find this in these locations all around the globe. You can submit this through these batch queries. But at the same time, you can actually, through a GeoServer, connect in real time, maybe not quite as powerful, to the whole 6 petabytes and get access to real-time data. Okay, sometimes people ask me, oh, and that's a good question, right? They're saying, oh, yeah, but what you're doing is you're just bringing all the data together, and yeah, you integrate it and you make it more usable, but that's never gonna work, right? Because people don't want to put data into one place. And that is true. And I think that is a really good point. So it is actually one of the unsolved problems in big data analytics, especially as it relates to climate data. So how do I federate across different clusters? And in this case, we actually do have several pair systems, right? So I talked about these different rows of data nodes, and we have actually different pair systems in different data centers. So how do we federate this? And so this is ongoing research. But today, even if a user starts requesting some data and they do some querying and they want to get some data from this data center and from this data center, and maybe you want to filter the data from data center 2 with data from data center 1, we have ways of doing this. How to do this best is still a research question, but that's something we're actively working on. Now let's look a little bit under the cover. So now I told you, right? So we have all this climate data. It all comes from these different places. They all have different resolutions, formats, projections. How on earth are you dealing with all this? And it's a very simple invention, but you're going to see how this innovation actually propagates through the system and why this is actually not such a bad idea. Of course, we have a global spatial temporal reference system, meaning any data which comes in is not being copied. It's being curated. And what do we mean by curated is we're basically putting it onto a standard spatial temporal reference grid. And we do this in space and time. So that means we gotta change the original data so it can fit onto that grid. And we have processes and looked into, and actually it's all automatic to do this, where we basically create more dense data, because that's what you have to do if you don't want to use substantial information. But the way these resolutions are designed are such that they're all nested. Why is that a good idea? Well, if they're nested, that means if I want to query or filter one layer with the other, or want to do a calculation with one geospatial layer to the other, I don't have to do any processing. I can do it immediately. So it is, in the true sense, a data cube. In fact, it's not a data cube at the end what we're generating. So we have these nested resolution layers. People will say often, well, no big deal, because data cubes in this community are actually well known. That's fine. Now, this data cube is indeed organized in a key value. So how does that work? So think about some data, and this could represent the world as you've seen here, right? Everything is in boxes, and then you have these nested resolution layers, and this goes all the way from centimeters to kilometers. And so you have all these nested resolution layers. So let's take a layer to just simplify it. And of course, the way you organize it is so some Z-order arrangement for obvious reasons. But then every one of those pixels here is a key, has a key. And the key is something magic. We published a few papers, but all the IP, all the thinking has to go into that key, because if you put the right information into that key, your system is really fast. Otherwise, it isn't. So, of course, it's space, it's time, other dimensions, etc. But then what we do to accelerate this further is not only other data is in different nested resolution layers, but the same data is also represented at different resolution layers. So we call them overview layers. Now, people are going to say overview layers is nothing new. Yeah, that's right. But then, of course, in these overview layers, we basically store statistical measures of what is under the next lower level layer. That's what we do. And why is that good? If I look for certain information and I want to search the globe, and I have my satellite data set, I'm going to start searching at an overview layer and then work my way down rather than running all that search on the highest resolution layer, right? And so that is how it works. The other really cool thing of this whole setup, and I was mentioning early, is given these are now all key value pairs, I can use I can use, of course, something like an HDFS system, a Hadoop system, be using an H-based system, which is basically a version of a key value store for columns. And then I can have connectors. I can connect Spark to it. I can run everything in parallel because everything is chopped up. So which means I can parallelize all my computation really efficiently. So that's in essence how it works. Now people are going to be asking me, well, does it really work? Here's a very basic example. And I'll show you a little more complicated examples in a second. But here's an interesting example. So let's say you wanted to do something really basic, right? You're a researcher and you want to get some data, and they have these different platforms. So for example, our friends at the USGS, they have this Earth Explorer. Then we have Pairs. Of course, Pairs, it's curated. And then ECMWF is a European platform. For people who don't know, that it's actually the European Weather Service. And you can see for accessing 1.6 gigabytes, you can look at the query times and you can see massive improvements. And the reason is not because there's some magic, it is because this has been engineered away from file-based distribution systems to key value, leveraging overview layers, etc. And this is all, these numbers are all actually batch mode numbers. I told you before, you can also get all the information in pairs through real-time, which is actually even faster. Okay, now, maybe I get later this question, but if you look into sort of the classical competitive systems, for example, people are using something like Google Earth, and they have done a fantastic job in way before we have in actually understanding how important it is to accelerate data access and data analysis of climate data. But even there, if you look into sort of the key, what I call emerging workloads, meaning I want to get time series from a lot of satellite data. I want to do complex spatial joining. Spatial joining means I want to take two different data layers. Let's say it's weather data and satellite data, and I want to filter one data layer with the other. Or I want to get not in a batch mode, but in real-time mode data. Or if I want to launch a calculation within a query, and you look at the performance, and this is published in this paper actually, you can get enormous enhancements through information architecture, as I described on the previous charts. So you're talking orders of magnitudes of acceleration. Here's sort of just to give you a more concrete example, and then we probably should try to see what I can wrap. But let me give you a sort of more concrete example here. And it is a toy example, I admit it, but it shows you what is possible if you use the right technologies. And that's really what we need to do in IBM, right? There are many experts in climate modeling and so on and so forth. So our role really is more, how can we help with the acceleration? So I give you an example. You know, of course, and we talked about this in the beginning, climate change, right? And you have seen these charts, or maybe you haven't seen the charts, but if you haven't seen them, they're all over the place. But basically you can see historically, boom, you get this huge increase in temperature, surface temperature. Currently we're actually at 0.04 degrees per year. Now, but that's of course around the whole globe, right? And sometimes you wonder, you know, is this weighted? Is this weighted to where people live? What does that really mean, right? Etc. Now, here's what you could do in pairs. And that's very simple. It's through these technologies. So there are actually fairly, there are these curated data sets which we have in pairs. One data set comes from the Europeans, which is called ERA5. It's a fantastic data set. It's probably the best, they call them reanalysis data sets. So these are data sets which tell you the weather, the historical weather over the last 40, 50, 60 years sometimes. at every point around the globe as we got observations and we remodeled. That's why they call them reanalysis, the weather, because obviously we don't have observation around the globe. So to a large extent, this data set, ERA 5, it's a monster data set, is one of the best renderings of historical weather which we have around. So now we take this and saying, hey, I'm interested in maybe understanding this temperature change. So what you can do in Inpairs, it's something super simple. You have actually, you look up there are roughly 450,000 timestamps because it's hourly data. So it's hourly weather data for the last, in some cases, it's going down to 40 years. So it's an enormous amount of data. And each data point, because these are images, right? For every location across the globe, there are 4 million data points. So you take 4 million data points with 450,000 timestamps, and then every value has 4 bytes because it's a value, right? There's a temperature stored in that. That means, I'm sorry, this should be actually 450,000 timestamps. So you can run a regression. The beauty of this system is you don't have to download the data because we can use these frameworks such as MapReduce or Spark to tell the system, you know what? I just want to run a parallel calculation and run this and calculate a regression. So in essence, I'm running 4.5 million regressions over 450,000 timestamps, and I let the system do that, right? And you can do that. It's a very simple code, just a few lines of code. There's an SDK which we have, which makes this easier. And boom, after 26 minutes, and that's on a single thread, in the system, single thread means, of course, it's still parallel, but you just submit one query or one task to the system. You can calculate, in fact, quite nicely the regions around the globe. And it's consistent, of course, with other researchers find, but within 26 seconds, which are the areas around the globe based on the ERA 5 data sets, which have, where in the last, in this case, 30 years, the temperature has increased more than in others. And you're going to find around the globe that, for example, here in the US, the East Coast has gotten much warmer. The Midwest has been somewhat stable. West Coast, much warmer. Southwest, one of the areas hardest hit by actually these temperature increases is actually Eastern Europe. And so this was 26 minutes. Now, if you would do this the old way, one by one, image by image, you would be running this in 7 months. Now you can parallelize that, right? So in all fairness, but you're not talking, it will be very difficult to do this with any other way than in 26 minutes. So that's an example. Now, this is all historical data. So it really just gives you what has happened till this day, right? Now, of course, you can build a time series model and you can build this and so on and so forth. And of course, it immediately drives ideas for, it might be a feature, for example, these trends might be a feature for then an AI model, which you're going to use to do future predictions. I think because we're running out of time, I may stop here. There is much more, of course. I wanted to show more of the scalability. I wanted to show how we're going to put these things together for some real problems. I guess we'll do this all next time. How we're going to apply these techniques for example, real climate impact modeling, like flood models. How do we validate these flood models? What AI models are we using? How do we have ground truth detection automatically built into it? How do we take then the uncertainty of these models and make our models better? What are the techniques for scaling down? So today we just focus actually on this little thing here. But I felt like it would be probably more useful to go into one than to touch everything sort of high level. And I will conclude right here, and hopefully there are some tough questions.
Thank you so much. That was such a wonderful talk. Loved it. Thank you for being so concrete with examples and explaining the work you're doing there. So I'll open up some questions to the audience. Let's see, Shara Lampos has his hand raised. Shara Lampos, do you want to ask?
Yeah, thank you for the very insightful talk. My work is actually on resilience of food and energy infrastructures and data generation. So I have a couple of questions on that. I will start with the first one, and maybe if there is time, we can look back. I have found that many people and in different areas have seen this data gravity that you described very nicely. So I was wondering if you have kind of a metric for the value of data. So you may have a lot of data in something that you already understand, but very little data in something that is tangential, but you actually kind of need it for your analysis going forward. So I was wondering if all of these systems that you use to integrate and process all of this information have any notion of value and so on.
I think it's an excellent
usefulness.
I think it's an excellent question, right? You're asking. You know, think about it. We are actually, and it costs us money, right? We are actually ingesting data every day. So how do we know it's worth it, right? That's really the question. And we looked into that. There is not a single and simple answer, because I think, as you already alluded, data doesn't live in isolation, right? That's why actually geospatial is such an interesting example, because you may need to analyze something. There's a tiny amount of data, but that's the one you need in addition to all the other petabytes of data. So it's not just the size of the data. It's really, can you integrate them? Can you link? How much contextual information do you have available? And so we have a model, a very simple model, which we use to make decisions of saying, oh, we're going to maintain commercial data pipelines because it's worth it. And this model is, of course, nonlinear. So meaning that if you already have weather data and satellite data, and now you can bring in, let's say, I'm just making it up, you bring in some infrastructure data, houses and stuff like this, right? Building stock. That usually has a huge value because it complements everything else you have, right? Now, if you just have the building stock data, for example, right, for sort of hazard applications, then that in itself has less value because you would still have to integrate it, right? And it's another dimension of data gravity, because data gravity also means, of course, you've got to bring these things together for meaningful analysis. And each time you bring these things together, you enhance the value of each other. That is why I think, just to answer, it's a long winding answer, but that's why I think the holy grail, and I'm not saying we solved it, but the holy grail of all this data gravity is really, in this space of climate, is really around federation. Who can solve that problem of massive petabyte scale federation in the most efficient way is at the end of what's going to drive enormous value of all these different data sets, because that's what you need to do. Sooner or later, that's what you need to do. Any other questions?
Yeah, Hendrik, this is Yuri here. One question is, how would people gain access to Pairs if they wanted to use it?
There's an academic license. Yeah, I would. I mean, if people want to get access, they can contact me. I'm going to connect them to someone who's going to give them an academic license. It's at the end, it's just a user password API key. There is a SDK that's open sourced. There are also some open source activities, and that's all you need. That's all you need to do this experiment I was talking about the right, for example, to run this query, right? This is basically a very simple example. There's actually, it's even one of the examples we publish to get people started. So all you need is an API key and your user ID, and you can get going.
Thanks.
I think we have Juan has a question.
Yeah, thank you very much. Excellent talk and super impressive results you got there. Have you, is it part of a pipeline right now to do featureization of the data? And particularly, I'm particularly interested on the amount of redundancy that exists in the data and how that can be leveraged to speed up the process even more, like to deal with a layer of information that is significantly smaller than what you're dealing with now.
So on the featureization, this is actually a very interesting topic, and we could have probably just spent on that topic. That's right. We have a whole set. You see, climate and weather data has its uniqueness as it relates to featureization, right? And a lot of these featureization cases are also use case inspired. Yeah, but we have a whole library of models who help with accelerating featureization. So it could be something as simple as like what I presented. Okay, so you want to feed these gradients of temperature change or precipitation change or combination or whatever, right? You want to aggregate, a lot of that has to do with spatial and temporal aggregation features. You want to compare something to climatology, or you want to feed something, you may not be interested. I think the gentleman before said he's interested in food system. You want to be looking now at the temperature gradients for all agricultural land in South America. But there's a whole set of this featureization work which is going on. On your second part of the question, I'm not exactly sure when you say redundancy. You mean redundant data, that you may have data from two different sources which may say more or less the same? Is that what you were referring to?
No, I'm actually talking about like things which are more or less stationary over long periods of time, so you don't have a lot of change, so you can exploit that intrinsic structure of the data to like reduce further.
Yeah, exactly. So, thanks for bringing this up, right? So, actually, yeah, completely right? So, for example, we do a lot of automatic detection with the system. So, an AI model detecting floods around the globe. Okay, good. Now, if you do that, often you have static information or redundant information, which you can use to crop or to inform your AI model much better, right? Or to rule it out, right? So, for example, certain detection algorithms are prone to, for example, for flood detections, prone to detect actually roofs of houses, etc. If you think about SAR satellite type of stuff. And we use that information, and it's one of those examples, I think, where I clearly feel where an advanced information architecture could help enormously, because in many of these AI cases, you already know much more about it. And then you use AI to find you make it harder on the AI than it actually has to be, because you have this contextual information, as I would put it, on geography or buildings or houses or roads or other things which don't change, right? They're already there. So why do I need to detect this? So I think that's if that's what you meant, that's another area where we actually use this technology quite a bit.
Thank you.
Wonderful. I think David Mordecai has a question. David, are you there? Maybe we lost him, but I will also see if anybody else have.
Can David put a question on the chat?
Yeah, he did put a question in the chat. Okay. Does the repository include mesoscale 2 kilometer to 400 kilometer data from raw radar and optical atmospheric scattering fields?
Yeah, there's there is radar data, and this is actually a set of researchers. There's some optical atmospheric scattering data in it. Not exactly sure. So there, to answer that question, on the first one, there is raw radar data. In fact, we used a research group in the UK used it. We have been collaborating to track actually, I think, bird movements and that kind of stuff. On the optical atmospheric scattering fields, I don't think we have that much. By the way, just want to say the system is open, right? It has user-enabled data uploads. So you can build your own data pipeline. Some users are doing it, then they push this data in it. And sometimes we work actually with our users and then it becomes part of the production pipeline. But there's a whole process. These are options if there's a more general use of this data, but I don't think we have optical atmospheric scattering fields.
Great. So I have a question. So when you describe this key value pair system as a way of like really getting access to the data much more quickly, but then you're also bringing up how, ideally everything would be just in one big repository, but you don't have that. People don't want to have all of their data in one place. And so you have these, data coming from different entities. Do you ever work with those entities to help them at least put key value pairs into their own systems so that even though it's still a separate node, you can at least have that be as optimized as possible? And then it seems like maybe some people don't really know how to handle their data, so then you would be actually helping them out and helping your system out at the same time.
Excellent question. The answer is yes. We work with a set of organizations, government organizations in most parts, exactly on that, right? And the benefit you have, as you say, a lot of organizations, of course, have that mission to disseminate their data more efficiently. And so then the question is, this allows you a complete customization. So you're not disseminating your data anymore by letting people to drink out of the fire hose. You can actually federate it. We actually do have federation today, but not the most efficient federation. But you can also access, of course, the commercial pairs or the academic version of the pair system and bring it together. You're completely right. Now we're working with actually a bunch of organizations around the globe to do exactly what you said, Jackie.
Okay, cool. Then I actually have one more question, which is, that was very interesting that you're talking about detecting floods. It's a really good example of like climate change work that's important. I was curious, like with the AI models that you're building, if you can also predict the floods, like so before they happen.
Yeah. So at the end, the way this works, I didn't get to it, is the way this works is there is you probably got a gist of it. We basically are focused on tools. And I know that's maybe not the most exciting thing for some of you, but we are really focusing on tools. But we have this, we call it climate risk and impact modeling framework. At the end, it is really a geospatial framework. But what it does is, it's all automatic. And if you would have time, I could have gone into this. It doesn't have to be floods, but we have flood detection. And we have our predictions. And how are we doing the predictions? Of course, the predictions we do with what we think the rain is, or what we think the precipitation. Let's talk about fluvial floods for 1 second. What the predicted rains are. So we have all that data. IBM has its own actually weather predictions from the weather company. We create simulations, and then we use it to validate it. And then we have an automatic parameter calibration, because there's lots of stuff you don't know. And then what we're trying to do is we're trying to look into what parameters could we adjust to minimize the uncertainty of that flood prediction, at the same time driving up the accuracy. And so this is all automatic. So we have this loop basically. And that's how it works. And in fact, we just came out with a commercial product, which actually does this whole 9 yards, where you basically detect the floods before the event, after the event, you compare it to your measurement. You have some clever techniques to adjust all the unknowns, because there's all these unknowns you have. In fact, it's just not a simple problem to do. And then you drive this up and drive this up.
Wonderful, thank you. Let's see. Well, I guess we have run over our time, and thank you so much to the audience for asking so many great questions. And Juan's clapping, not raising his hand. Okay. Anyway, I just loved this talk. Thank you so much. We really, really enjoyed. It was such an honor and a pleasure to have you here. And I'm sure that everyone in the audience learned a tremendous amount.
Yeah, thanks for having me. And I just want to point out the one thing, of course, this work I presented, there are many people involved in here, right? And I just want to say, this is a big team we have. It's a team actually around the globe here. Maybe if I may just show this one shot, is too many contributors to leave, but we have actually contributions of this work here from all over the globe. Yeah, thank you.
Thank you so much. Great talk.
Thank you so much. Okay. Take care.
Thanks, Hendrik. Tschüss.